Hello, everyone, and welcome back from what was hopefully a relaxing and refreshing Easter vacation. I hope you got in contact with some friends and family that you haven't talked to in a while and just were able to relax and enjoy your time off, especially under the circumstances we're under at the moment. But we are back and we're jumping into chapter 17, which is non-renewable energy. I've set it up so that you guys can read along in the textbook with me as I go, for those of you who would like to read while you listen. But before we get started, we're going to, of course, start with a chapter vocabulary. Our vocabulary for this week is energy, kinetic energy, potential energy, combustion, energy efficiency, renewable energy, non-renewable energy, and electricity. So that will be available for you to copy over from the answer key that is posted on LMS or that you got in your email. So by the end of this chapter or section, lecture, we will should be able to define energy and differentiate between kinetic and potential energy. We should be able to identify different forms of energy. And then lastly, we'll describe how human society uses energy resources. So for Monday, let's go ahead and get started with an overview of energy. So this is lesson 17.1, energy, just an overview. So we'll cover this Monday and Tuesday of this week. So Kitty Hawk, December 17th, 1903. On a wide-swept beach in North Carolina, a small, fragile airplane piloted by Orville Wright rose into the air. As his brother Wilbur held his breath, Orville managed to keep the tiny airplane aloft for 12 seconds, flying 36 meters or 40 yards across the sand. With that short flight, the Wright brothers forever changed the way people travel and transport materials. Today, huge jets carry passengers and cargoes across continents and oceans. The Wright brothers' tiny plane and modern jets are different in many ways, but they share some characteristics. For one thing, they both need fuel to fly, and the fuel they use comes from petroleum. Today's jet is much bigger and travels much faster and farther than the first airplane. Therefore, a jet uses a lot more fuel, and the plane that took to the air at Kitty Hawk. And if you're looking over at the right side of your screen, you'll see an image of the first flight. This aircraft was powered by gasoline, and the Wright brothers were responsible for its design and flight. So on our PowerPoint, we have the United States has only 4.5% of the world's population, but uses 21.1% of the world's energy. And that, again, is a statistics as of the date of the textbook, which was 2011. So what is energy? Fuel supplies airplanes, big and small, with energy. Energy is the ability to do work or cause a change. Airplanes do work when they move from one place to another. Energy from the sun changes Earth by warming the atmosphere. The sun's energy also causes a change when in photosynthesis, it powers chemical reactions in which carbon dioxide and water combine to form food molecules. Energy ran the printing presses that printed this book, and energy enables you to turn these pages. And without energy, you couldn't read the words in this paragraph. Energy is necessary to change the position, composition, or temperature of something. Most forms of energy fall into one of two categories: kinetic energy or potential energy. Kinetic energy, for example, is our figure B. So as this girl is zooming down this ski mountain and skiing down the mountain, she is exerting kinetic energy. Whereas when she is sitting at the top of the hill, she is not in motion, and that represents potential energy, because she has the potential to release energy, and she does so as she skis downward. So kinetic energy. On a bright winter day, a skier zooms downhill. The fast-moving skier has kinetic energy. Kinetic energy is the energy that an object has due to motion. A whizzing baseball, a train speeding down a track, a jumping frog, and a wave crashing on the beach all have kinetic energy. You can think of kinetic energy as energy in action or energy in motion. Potential energy, on the other hand, occurs before the skier took off. She stood at the top of the hill. At that time, before she started moving, she had potential energy, because objects that are high up tend to go downward. Potential energy is energy that an object has because of its position or shape. In contrast to kinetic energy, potential energy is the energy that is stored. A stretched rubber band has potential energy. When you release the rubber band, it jumps away from your hand. The rubber band now has kinetic energy because it is moving. Forms of energy. It's a warm, sunny Saturday, so you and a few friends decide to hike to the top of a hill. You call your parents on your cell phone to let them know what your plans are. Then you pick up your backpack and start climbing. When you get to the hilltop, you and your friends break for lunch, and you eat the sandwich that you packed. On your hike and the lunch break that followed, you use several kinds of energy. Energy comes at the lunch break that followed. You use Energy comes in many forms, and each of these forms can be converted into other forms. The first of which is mechanical energy. The motions involved in picking up your backpack and hiking involve mechanical energy. Mechanical energy is associated with the motion and position of an object. While a moving baseball has mechanical energy that is kinetic, so do a speeding bike and a car moving down the street. A compressed spring has mechanical energy that is potential. When you release the spring, the stored energy becomes kinetic and the spring moves. So mechanical energy is associated with the motion and position of an object and can be kinetic or potential. Kinetic meaning moving, or potential meaning being still. Electrical energy. A cell phone uses electrical energy to send messages. Electrical energy is energy associated with electrical charges. Electrical energy stored in a cell phone's battery is potential energy. When you use the phone to make a call, the energy is kinetic. Electrical energy powers many things you use, such as light bulbs, computers, DVD players, and hair dryers, just to name a few. So again, electrical is associated with electrical charges and can be kinetic, moving, or potential, stored. Thermal energy. All materials are composed of tiny particles called atoms and molecules. These particles are moving all the time. Thermal energy is the kinetic energy of all atoms and molecules in an object. The more energy the atoms and molecules have, the faster they move. If the particles in an object start to move faster, the object will become warmer. The particles in hot volcanic lava move very fast. So thermal, kinetic energy of atoms and molecules. The faster the atoms and molecules move within an object, the warmer it becomes. We do have some other types of energy. They include electromagnetic energy. When the sun warms you or you cook food in a microwave oven, you are experiencing or using electromagnetic energy. Electromagnetic energy travels through space in the form of waves. Visible light is a type of electromagnetic energy, as are radio waves and ultraviolet radiation. Chemical energy. The food you and your friends eat while hiking provides your body with chemical energy. Food such as corn is made of molecules, and chemical energy is stored in the bonds that hold the atoms together in molecules. When bonds in the molecules break, energy may be released. Chemical energy is potential energy because it is stored in chemical bonds. When you move your leg and arms during hiking, your body converts chemical energy stored in food into mechanical energy. Like food, fossil fuels contain energy stored in the molecules of chemical compounds. Last, we have nuclear energy. Chemical energy involves bonds between atoms. Nuclear energy, in contrast, involves forces within atoms. The nucleus is the central part of an atom. The forces that hold nuclear particles together in the nucleus can store a huge amount of potential energy. You will learn more about nuclear energy later in this chapter. All right, so look over on your left side and we're going to look at a quick lab. So where's the energy? So the first thing we want to do is get a flashlight, and we're going to check this guy out, and we're going to see if he works. All right, so we have our flashlight and it's working. Now we're going to go ahead and remove the batteries. Alright, so we've taken out the batteries. And now we'll try to turn it back on and see if there's any leftover energy. Nope, no energy. Alright, so now we'll go ahead and place the batteries back in the flashlight. And we can see that it is working again. Alright. So we can just leave this on, and it says after a while to place your hand on the bulb of the flashlight, and what do you feel? What you're going to feel if it is a traditional light bulb especially, you'll feel this much sooner, is that you'll feel that it is warmer than the surrounding material. And if it's a traditional light bulb, it can actually burn you, so be very careful. You don't ever want to touch a light bulb, like a fluorescent light bulb that has just been turned off. It will be very hot. This is actually an LED light bulb. Those release significantly less amount of heat, so I actually cannot even feel a temperature difference with the LED light bulb. Which also translates to less energy being lost. So let's look at our analysis and conclude. So our first question is to infer. When the flashlight did not have batteries, what happened when we switched on the flashlight? Well, when there was no batteries in it and we turned the flashlight on, nothing happened. That's because there was no stored energy available to create an electric current and power the light bulbs. So nothing happened. Number 2, relate cause and effect. After we inserted the batteries into the flashlight, what happened when you turned the switch on and why? Well, of course, we saw that the light bulb, the light came on, and that's because we put in the batteries, which are a stored, and right now it's potential energy because it's not being used, and it is storing energy that can be released whenever I turn on the flashlight. It will release that stored energy in the form of electrical energy, which is number 3. What form of energy lights a flashlight bulb? And that's electrical energy. 4, use analogies. How is a flashlight battery like a box in which you put baseball bats when they are not being used? Well, again, we are emphasizing that we're relating the battery to a box, and that box would be storing bats, and they're both storage, right? A battery is just a storage of electrical energy, and just like that box would be a storage place for the bats that it was containing. All right, so that was our next forms of energy were electromagnetic, which was kinetic energy that travels in waves, chemical, potential energy stored in molecular bonds, and lastly, nuclear, which was potential energy stored by forces that hold atomic nuclei together. Go ahead and stop here and complete in your workbook questions 1 through 14. All right, next we're going to be looking at energy conversion and efficiency. So energy conversion. Energy can be converted or changed from one form to another. For example, when you turn on an electric fan, the blades of the fan turn around. In the fan's motor, electrical energy is being converted to that mechanical energy. The mechanical energy in the moving blades produces cooling breezes. Another example is when fireworks explode in the night sky, chemical energy has been converted to thermal energy and electromagnetic energy. The electromagnetic energy takes the form of a brightly colored light display and patterns we associate with fireworks. So we have combustion. Combustion is how we see in the image on the PowerPoint was combustion of gasoline was used to power the first airplane as it flew over the beach in Kitty Hawk, North Carolina on December 17th, 1903 that we covered at the beginning of the chapter. So what is combustion? Combustion is another example of energy conversion. Combustion is the process in which fuel burns because it combines rapidly with oxygen. So chemical energy stored in fuel is converted to thermal and electromagnetic energy, and we feel the thermal energy as heat and see the electromagnetic energy as light. We have a combustion equation. Many substances can serve as fuels. The fuels that we are most familiar with are wood and fossil fuels such as coal and oil. So the chemical equation for combustion of natural gas and fossil fuel composed mostly of methane is shown in our textbook, which is CH4 plus 2 oxygens equals carbon dioxide and 2 water molecules. So methane plus oxygen equals carbon dioxide plus water. The principal products of combustion is of methane and of other fossil fuels are carbon dioxide and water. Both carbon dioxide and water vapor are greenhouse gases, if you remember. So what about energy efficiency? And airplanes, cars, and fans all require energy to do the jobs that are designed to perform. However, not all the energy supplied is used to do the work for which it was intended. In a car, for example, some of the energy supplied by the fuel is converted to heat rather than motion. Energy efficiency is an expression of how much of the energy put into a system actually does useful work. Energy efficiency is usually expressed as a percentage. For example, if an automobile has an energy efficiency of 15%, only 15% of the energy provided by the fuel actually moves the car forward. So, sources and uses of energy. Highly industrialized nations such as the United States use an enormous amount of energy. Where does the energy come from and how is the energy used? Well, renewable and non-renewable energy. Energy resources can be divided into those two broad categories, renewable and non-renewable. Sources of renewable energy are nearly always available somewhere on Earth's surface, or they are replaced in a relatively short time. Renewable energy resources include the sun, wind, moving water, wood, and heat that comes from deep within the earth, which would be geothermal energy. Sources of non-renewable energy, in contrast, cannot be replaced. Non-renewable energy resources include fossil fuels such as coal, oil, and natural gases, as well as nuclear energy. Once these resources are used up, they are gone forever. All the renewable and non-renewable energy resources identified above are primary energy resources. Primary energy resources are found in nature. Electricity, on the other hand, which is energy made available by the flow of an electrical charge, is considered a secondary source of energy because it must be produced using a primary energy source. For example, electricity can be produced by burning coal. Electricity is useful because it can be transferred over long distances and used in many ways. So there are four main uses of how energy is used. We can see in the graph at the top of your textbook that we have 19% is used for commercial purposes, 31% for industrial purposes, 28% for transportation, and 22% for residential. So how energy is used? The U.S. Department of Energy, or DOE, identifies four general ways that energy is used in the United States. As we saw in Figure 5, energy is used in industry, transportation, residences, and commerce. In industry, energy is used to accomplish jobs such as constructing buildings and making products. Transportation vehicles that use energy include cars and trucks, and of course, also boats, airplanes, trains, and even motorcycles. Residences, including your apartment or house, use electricity to run appliances, light bulbs, and electronic devices. Commercial uses occur in places where business is conducted, such as offices, supermarkets, and shopping malls. We have a worldwide patterns of energy use. So developed nations generally use far more energy than do developing nations. Per person, nations with the most industry use up to 100 times more energy than do nations with little industry. The United States has only 4.5% of the world's population. However, it consumes 21.1% of the world's energy as of 2011. Developed and developing nations also tend to use energy differently. Developed nations use about 2/3 of their energy on transportation and industry. In contrast, developing nations use most of their energy to provide the basic necessities of life, such activities include farming, preparing food, and heating homes. All right, so let's take a look at our Lesson 1 assessment. So this completes our Monday and Tuesday lecture. So number 1, compare and contrast. Contrast kinetic energy and potential energy. Give an example of each. So kinetic energy, again, if I can remind you of the girl skiing when she was skiing down the hill, and she was considered to have kinetic energy, and that is because she was in motion. When she was sitting at the top of the hill before she was going to ski down the slope, she had potential energy, and that is based on a object's position or shape. So because she's at the top of the mountain, the gravity is going to pull her down, so she has the potential to create that kinetic energy. Some other examples of kinetic energy is a basketball bouncing. Another example of potential energy is a basketball being held above the floor. Now, if you just have a basketball sitting on the floor, that is not considered to have potential energy unless it is on an incline, and then of course the ball is round. So if there was a force holding it from rolling, it would have potential energy. If you remove your hand or whatever was blocking the ball, it would then have kinetic energy. But if it was a flat object sitting on a flat surface, it would not have any potential energy. Number 2, relate cause and effect. Carbohydrate molecules are found in foods. These carbohydrate molecules provide your body with energy. How does this happen? And that is, energy is released when the bonds of carbohydrate molecules are broken apart. So that carbon-carbon bond that's being broken down during your metabolism, whether it's during photosynthesis in a plant or during respiratory when you're consuming, when you're moving around and creating mechanical energy, you're using the stored chemical energy that from the food that you ate, and your body is breaking those molecules apart, releasing energy that can be used mechanically by your muscles. Number 3, explain why is electricity considered a secondary source of energy? And that's because it's not found in nature. It is created by the consumption of other resources like coal or burning wood. And number 4, is the energy contained in fossil fuels potential energy or kinetic energy? And explain. Well, it is actually potential, and that's because it is stored energy, right? Once you apply heat or cause combustion, then it can be released as different forms of energy. All right, guys, so that completes chapter 17.1, Tuesday's lecture. Go ahead and complete your workbook questions 15 through 19. And tonight's homework, you can either go on www.pearsonrealize.com and complete the homework. There, it's a multiple choice homework assignment on chapter 17.1 or printed from your email.